Hello, everybody, and welcome to your channel Thermal Engineering Concept and Principle. This is Professor Ali Tarrad. In this episode and series of different videos, we will talk about an application in the field of thermal engineering, which is the most important application in our heat transfer topic. What are the structural components of shell and tube bundle, heat exchangers, and how do they work? In this series, we will talk about this type of heat exchangers and how can we predict the thermal design of such heat exchangers. Welcome again to your channel Thermal Engineering Concept and Principle. In this episode, we will continue to present what we have started before about thermal design of heat exchangers, especially the shell and the tube heat exchangers. In this episode, we will introduce a complete thermal design of the shell and tube heat exchanger with multiple choices of heat exchanger configurations and specifications. Thank you for your continuous support, and I hope that I will introduce some information that are useful to everyone who works in the field of thermal engineering. From our introduction, we knew that the objectives of the present episode are related to a practical case study from industrial field where a thermal design of heat exchanger is required. And then we will arrive to the summary of the present episode. Practical case study. Let us consider a shell and tube heat exchanger where it is used for cooling down engine oil. It enters the exchanger on the shell side at 60 Celsius and leaves at 40 Celsius. At a flow rate of 5.156 cubic meter per hour, measured at the mean temperature of the oil. On the tube side, cooling tower water is used for the cooling purposes. It enters the heat exchanger at 30 Celsius and returns to the cooling tower at 35 degrees Celsius. Design the heat exchanger according to TEMA standards. We have some information given, or we have to start with these assumptions of physical, geometrical parameters. Let us consider a tube, a stainless steel tube, 316, that is 16 Birmingham wire gauge with outside diameter of 15.88 millimeter and inside diameter of 12.57. The metal thermal conductivity of 16 watt per meter Kelvin, a square tube layout at 90 degree as shown in this diagram, with a tube pitch of 1.25 times the outside diameter as shown in these values. And we have an assumption to choose any of these standard lengths of the heat exchanger, 1.22 meter or 2.44 meter or 3.05 meter, to design this heat exchanger, and select a buffer spacing according to the design requirements, with a buffer cut of 25% at and the fixed tube sheet is selected for this heat exchanger. And finally, we have the water fouling coefficient of 3000 watt per meter square Kelvin. And for engine oil, we have the fouling resistance, that is 0.18 times 10 to power minus 3 meter square Kelvin divided by watt. Here we have the thermal properties of the oil engine and cooling water. These properties were obtained at the mean temperature of the fluid or the bulk temperature, and we are going to use these thermal properties in our design. Solution for this practical case. We will pass through thermal design number 2 because we have already passed through thermal design number 1 in the previous episode for a single tube pass. The same procedure can be followed, that to start with the calculation of the thermal load of the heat exchanger, and using the flow rate and temperature difference with the thermal properties, we will get the load to be 50 kilowatt. And then we need to calculate the mass flow rate of water. Again, we have to follow the energy balance by assuming that the energy um, rejected from the oil to be absorbed by the water, the cooling water, and there is no heat loss because the heat exchanger is well insulated. Then we will get the mass flow rate of water uh, to be 8.224 cubic meter per hour. And then the first step, we have to calculate the LMTD of the heat exchanger for both flow sides. Delta T1 equal 25 and delta T2 equal to 10 Celsius. Then the LMTD will be 16.37 degrees Celsius. Of course, because we are dealing with more than one pass for the tube side, we have two tube passes, then we need to get a temperature correction factor from the figure shown. The first step to calculate R and S, and we take these two values and enter this figure. Then we will get the correction factor to be 0.93, and delta T mean equal LMTD times F sub T. Then we will get 15.22 degrees Celsius for the mean temperature difference. As a first trial, for the design, let us assume that the overall heat transfer coefficient to be 200 watt per meter square Kelvin. Then this will allow us to calculate the surface area of the heat exchanger, that A naught equal Q dot divided by U naught delta T mean, and that will produce a value of 16.42 meter square. And we may reflect that on the number of tubes per pass to be A naught divided by pi D naught L sub pass times number of tube passes. Then we will get number of tubes, 68 tubes. The shell size can be estimated from the knowledge of the tube pitch and with the help um, of course, the tube pitch will be reflected on the size of the tube bundle, and we may calculate even the equivalent of the shell side to be 15.68 millimeter, and the bundle diameter and shell size d sub b equal to d naught times this parameter n sub t, total number of tubes divided by k1 to the power 1 over n1. Of course, we have a table that is prepared for these coefficients, k1 and n1, depends on the shape of the tube layout and tube pitch. For our case, for two tube passes, we have the square pitch 1.25 d naught, then K1 equal to 0.156 and N1 equal to 2.291. And if we use these coefficients in the general form of a tube bundle, then we will get 305 millimeters. We need to estimate the clearance between the outer diameter of the bundle and the inner diameter of the shell with the aid of bundle diameter and fixed tube sheet and U-tube curve. We may get clearance gamma equal to 12 millimeter. Adding this value to the tube bundle diameter, we will get a 317 millimeter. Of course, with the aid of this table, we may find that the nearest size of pipe to be used as a shell is the 14-inch pipe schedule standard with the inner diameter 336.54 millimeter and uh, a shell thickness of 9.53 millimeter. Now let us go to estimate the heat transfer coefficient on the tube side with the aid of water velocity, which equals to 0.271 meter per second. We may estimate Reynolds number to be 4,430.2. And with the aid of Tarrad's correlation as shown in table 2 in the next slide, we may estimate Nusselt number to be 0.02, Reynolds number to power 0.8, Prandtl number to power 0.5. Substituting the corresponding values, then we will get Nusselt number to be 37.39, and from the definition of Nusselt number, we may get the heat transfer coefficient on the tube side to be 1853.1 watt per meter square Kelvin. Turbulent flow correlations. In fact, there are good number of correlations available in the open literature, but I have selected in this table 5 of them, started from Cedar Tat in 1936 until we arrived to Tarrad in 2004. All of these correlations are represented uh, in a series of parameters used in these correlations, such as Reynolds number, Prandtl number. And every correlation has its own limitation. It depends on Reynolds number and the Prandtl number. For example, for Cedar Tat correlation in 1936, It is applied for Reynolds number greater or equal to 2300 or less or equal to 10 to power 7. And the Prandtl number should be greater or equal to 0.5 within the range to equal or less than 120. And if we go down to the last correlation as presented by Tarrad, it is applied for Reynolds number greater or equal to 3000 and less or equal 5 times 10 to power 5. Of course, all of these correlations are applied for turbulent flow conditions. And we have T sub B bulk temperature equal to inlet plus outlet divided by 2 as a mean value. And the film temperature depends on T wall plus T sub B divided by 2. And these correlations, of course, require the knowledge of the thermal properties of these fluids. We are going to use one or two of these correlations in our present application. Let us estimate the oil viscosity depending on the wall temperature. Of course, we have previously in previous episode have derived an equation to estimate the wall temperature to be in the form of equation 5, and it has been used with introduction of these values for different parameters to be T wall or T naught equal 35 degrees Celsius, and that will help to give oil properties at this temperature. We have pneumatic oil, that is the kinematic viscosity to be 0.405 times 10 to power minus 3 meters square per second, and the density to be 879.1 kilogram per cubic meter. And if we multiply the density with the kinematic viscosity, then mu oil to be 0.356 kilogram per meter second. And if we use or select a buffer spacing of 200 millimeter, then we may calculate the cross-sectional area to be 0.01347 meters square, and the mass velocity of oil on the shell side to be 92.5 kilogram per meter square second, and then the velocity of oil on the shell side to be approximately 0.106 meter per second. Using the mass velocity, then we will get the Reynolds number to be 10.42. Of course, we need to predict the heat transfer factor for the shell side. We use the Reynolds number with the baffle cut of 25% of the baffle. Then we will get J sub HS equal 1.95 times 10 to minus 1. By using the general form of this equation to predict the heat transfer coefficient on the shell side, including the effect of temperature on the dynamic viscosity as shown at the last term of this expression for Nusselt number, we may estimate Nusselt number to be 28.95 uh, on the shell side, and that means we may get the heat transfer coefficient of oil on the shell side from the definition of Nusselt number to be 262.2 watt per meter square Kelvin. Now let us calculate the overall heat transfer coefficient from this expression. Then if we substitute all values which we have calculated during this procedure, then 1 over U naught calculated equal to 0.0052 meters square Kelvin per watt. And that means we may get U naught calculated to be 192 watt per meter square Kelvin, which is less than the assumed value. That means we have to go in multiple trial and error to find the calculated overall heat transfer coefficient depending on assumed value. And usually such design uses codes, computerized program that will minimize the effort and speed up the calculation, and you may get many designs for different parameters at the same time by using that program. After repeating the calculations, we got the final results to be in the form of this table. And we have started with U naught assumed 200 and then ended with a calculated value of 190 with a tube length of 2.44. Then we have reduced the value, the assumed value, to 175 with the same tube length, and the estimated value was 189.3. Of course, this is an accepted design because the difference between the assumed and the calculated value is almost similar, and usually we use about 10% for the tube size or the heat changer size to for a safety to compensate for the safety. The question, is there any other design of this case study? The response will be yes, and we have used a tube length of 1.22 meter with assumed value 200 and the buffalo spacing 200 millimeter. Then we got a value of 215.1, and this is an acceptable design without repeating these calculations. Um, I will be happy to help if you can start your design for two tube passes by using 3/4 inch stainless steel 316 with the 16 Birmingham wire gauge, and just try for practice, and then we will get a final design. And if you need any help, please ask through the site on the YouTube. And I think we have arrived to a proper design for this heat exchanger. 1.22 is a quite good design for two tube passes. Number of tubes 270, and let us see how can we make advantage of the information given in this episode to help you in the field of application and your work. Now we have arrived to the final part of this episode, that is the summary. We focused on the thermal design of heat exchanger in a practical case, and we finalized that in a table. You may have a look back at this table and see the differences between the iterations which we have used and how we have manipulated the various parameters affecting the design and how we have arrived to the final stage of this design. We have also some references that could be used to support this video, and you may use them for enriching your knowledge about heat exchangers. And thank you for watching and continuing support. I will see you in the next part of this um, series of episodes about thermal design of heat exchangers. Bye bye.